Good afternoon, everyone. Welcome back. Today we're looking at the fourth and final day of solving optimization problems. This lesson can be found on page 13 of your handout. And what we're going to be doing today is two examples, but we're not actually going to complete the examples all the way to the conclusion of them. We're not actually going to find the answers to the problems. What we're going to do is use the two problems that we're going to look at in order to kind of summarize things in terms of equations of constraint and how they fit into solving a problem where you're trying to optimize a variable. So we have the following information. There are two problems associated with the same scenario. In both of these scenarios, we want to make a box that has a square base and an open top. And I will draw one of those for you in a second to give you a visual of what it is we're talking about. The difference between the two problems is in problem one, you need a certain volume. So the volume has to be 600 cubic centimeters. Why does the volume have to be 600 cubic centimeters? Well, we're just the manufacturer of the box. We don't question the client's wishes. The client may be making boxes that have to hold 600 cubic centimeters of sand. Why? We're not interested in that. We just know that the volume of the box has to be 600 cubic centimeters. And what we want to do to help the client out here is we want to minimize the amount of material. And the amount of material is going to be associated with the area of all of the sides of the box, because that's representative of the amount of material that the 3D printer is going to have to use to make the box. Now the second problem is different. We're still going to use a 3D printer to construct a box that has a square base and an open top, but this time we want the total surface area to be 2,000 square centimeters. And the reason for that is we only have a certain amount of the material that the 3D printer uses for each box. And the question in problem two is, what are the dimensions that will maximize the volume? So in problem one, we have a fixed volume and we're trying to minimize the surface area. In problem two, we have a fixed surface area and we're trying to maximize the volume. So these two problems may look similar, but they're entirely different in terms of what we're going to be doing mathematically. So the question is, for each case, write the equation of constraint and use the equation of constraint to write a function that can be used to solve each problem. And again, we're not going to solve the problem. We're just going to get to the point where if we were going to solve it, we would start differentiating. So if you take a look at this chart, this summarizes nicely the important aspect of each of the two problems. In problem one, the volume is fixed at 600 cubic centimeters, and we would like to minimize the area. But in problem two, the area is fixed at 2,000 square centimeters, and we want to maximize the volume. Well, let's talk about a box that has a square base and an open top before we go on, because we're going to need to imagine what this thing looks like if we want to come up with equations for volume and for surface area. Well, let's draw what the box looks like. Now I'm going to go back into my junior high industrial arts class and use a bit of the skills that I learned in terms of drafting on a drafting table, so you might want to hold off on drawing this until you see what I come up with. What I'm drawing right now are the two edges of the base of the box that we will be allowed to see. The other edges are going to be covered from view, so they won't be visible. But I am going to draw those other ones as well. So this represents the bottom of the box. Now don't forget it's square, so all four of those sides are the same length. Now we also have the same shape at the top of the box. But unlike the bottom of the box, you will be able to see all of the edges that form the top of the box. Then, of course, there's a height to this box. And that edge, which is visible, is also going to be visible here and here. That length is partially visible from that top left-hand corner only until it disappears behind the front of the box. Of course, I could add here that line extended down as long as I put that it is dotted. So this is what we are looking at, roughly speaking. We have a box which has the following dimensions. I'm going to call the length of the bottom x and the width of the bottom x. They're both x because that is a square base. We're looking at it at an angle, so your perception is off a little bit. It may not look like those lines are equal, but they are intended to be equal. The other dimension, the third dimension of the box, I'm going to label as h. Now, of course, that diagram might be giving you a headache, so if we eliminate those dotted lines, it starts to look more like what a box would look like. Now, both of these problems are dealing with surface area and they're dealing with volume. So it doesn't matter that the two problems are different. We should look at this box and see if we can come up with a formula to describe the surface area of the box and to describe the volume of the box. So we'll start off with the surface area. The surface area of this box is going to be found by adding together a number of rectangles. The base of the box is a square whose area is x multiplied by x, or x squared. If you were to take a look at the front of the box, or the side of the box, or the back of the box, and it doesn't matter whether you look at the left or the right side, those four rectangles are identical because they all have the same height, h, and they all have the same width, x. So the area of, for example, this side of the box is length times width, which is x times h. The area of this side of the box is length times width, which is x times h. All of these sides, all four of them, have an area of xh, which means that we have to add to the area of the bottom of the box, which is x squared, 4xh. And this is the formula that relates the area to the dimensions of the box. In order for us to define the volume, well, that's pretty easy. Volume is length times width times height for a rectangular prism. So we get volume equals x times h. And this is the formula that we would use in order to determine volume. So when we look at the problems, the thing we want to optimize in problem 1 is A, so we need a formula for A to differentiate. And the formula is the formula we've just developed, which is the surface area is x squared plus 4xh. When we look at problem 2, since you want to optimize, specifically maximize volume, you need a formula for volume to differentiate. And the formula for the volume is the one that we created, x squared h equals volume. The problem with both of these is we have too many variables in each of the equations. Specifically, we want to define area in terms of maybe just x and not x and h. And we want to define in problem 2 volume in terms of only x and not x and h. And in fact, we are going to eliminate h because it's going to be easier. Now, you could certainly, when you see how we're going to eliminate h, you could certainly try to eliminate x, but I think you would discover very soon after trying to get rid of x that your problems become more complicated in doing the work. You have more obstacles to get to the answer. Now, how are we going to eliminate h? Well, we're going to use the equation of constraint. The equation of constraint in problem 1 is that the volume, which is 600, has to be equal to x squared multiplied by h. The equation of constraint that we're going to use in problem 2 is that the surface area of 2000 has to equal x squared plus 4xh. In problem 1, h is equal to 600 over x squared. I would probably write 600x to the negative 2 to make my life just a little bit easier. And the equation of constraint in problem 2, in order for me to find h, I would have to take 2000 and subtract x squared, which gives me 4xh. Then I can divide every term by 4x, so I will get 2000 over 4x minus x squared over 4x equals h. Or better yet, h is equal to 2000 over 4 is 500, and we have x to the negative 1 minus 1/4 x. So in problem 1, you are going to have to take a equals x squared plus 4xh. You are going to have to take a equals x squared plus 4xh and put in for h (600x to the negative 2). Then you're going to simplify the resulting equation, and then you'll be set up to find dA dx and to find the critical value of x and use that to solve the problem. In problem 2, you are going to have to take the formula volume equals x squared h and replace the h in there with 500x to the negative 1 minus 1/4 x. Of course, then simplify the resulting equation and find the derivative in that equation. So in problem 1, you're going to be finding dA dx. In problem 2, you're going to be finding dV dx. We're not done yet because the problem actually did say develop a function that can be used. So we'll go one step further and do what I've just described. For problem 1, I have a equals x squared plus 4xh, but h is 600, x to the negative 2. So this isn't going to require a lot of work to finish finding the function that we would use in problem 1. The area will be x squared plus 2400 x to the negative 1. So that is the function that we would differentiate in order to solve the problem, which is what the example asked us to find. In problem 2, we're going to take the volume, which is x squared h, and we're replacing h with 500 x to the negative 1 minus 1/4 h, which is going to give me, when I expand that by multiplying the x squared through that binomial, will give me 500x minus 1/4 x cubed. And that would be the function that you would have to differentiate to find the answer to the problem. So we've answered the second part of this example. In the first equation on the left, you're going to find dA dx. In the equation on the right, you're going to find dV dx. I'll maybe work out answers for this and post it in our Google Classroom just so you know what the answers are. I'm not going to attempt to put exact values in Google Classroom because it only allows text. So I will put the solutions in there sometime later so that you can check them. So assignment 2 is ready for pickup. You know where to find it. It's in the shared folder. Look for the folder that says assignments. Look for the subfolder that says assignment 2. And inside of that, you will find your own personal assignment with your name on it. I believe I've put a due date on there of Wednesday, April 22nd. So you can be working on that. That's it for the day. Have a great rest of the day, you guys, and we will talk to you soon.